Hey guys, so I'm just going to continue on with what we were kind of going over in the last few videos. So hopefully by now, if I remembered correctly, in the other two videos, hopefully I went over 8 and 9 on the handout. Um, but one thing hopefully, or maybe I forgot to go over, was in the sigma notation here. Oh, sorry, if I can kind of get that on. Sigma notation, what this says is that you're taking the sum of the heights of the various rectangles with the bases. And then you estimate the base by taking the x coordinates in between. What x coordinates are you talking about for the area under the curve that you want, and you divide it by the number of rectangles that you want to get the bases here, or the lengths of the bases here, right? What I didn't show you was this. This n is very crucial because it basically tells you how many rectangles you want. So in this case, I wanted 3 rectangles. And on these examples, hopefully in the previous videos, I always wanted 5 rectangles. So n should have been equal to 5. Well, in your book, if you go back to your book now, you're going to see that they don't call this method Riemann sums, I think in the beginning at least. They call this the rectangular approximation method, or RAM as they call it. So they have like the left RAM, like LRAM. So if you can kind of see in this figure, they have LRAM, middle rectangular approximation method, and right rectangular approximation method, which is right rectangular approximation method, which is no different from the right sum Riemann sum, midpoint sum, and left sum Riemann sum. So it's the exact same thing. Okay, same idea with underestimations, overestimations, and like middle of the road estimation or estimations. It's the same thing. Now, what I want to discuss is at some point in your at some point in your book, they actually have a calculator program that you can kind of read through to how to program this. I'm not sure if it actually states in here. It's been a while since I kind of gone through this section, this book, but this is the number of rectangles, and then you can kind of see this is approximating the area under this curve, I think, and I forget what the parameters between an interval of 0 to 3. For between 0 to 3, they made this many rectangles. So they have an actual they actually have a program in which they can kind of calculate the Riemann sum and tell you if you gave it like the direction to either go left sum, middle sum, or right sum, it'll give you a total area measurement according to those which method you ended up using. And by the way, if you look up here, like up in the book, all of this should look really recognizable. It should look very similar to all the different approximations we were doing here if you look very carefully. You can just kind of suspect just from looking at the work here that 1/2 occurring in each of these values, that should tell you that the bases that they determine, equal bases they determine, are 1/2 big, and they did it for both the left sum, the middle sum, and the right sum. And then I think the f of x was x squared, and you can kind of see what the approximations came out to be. Middle sum came out to be literally in the middle of the left sum and the right sum, and so forth. But what I want to go over was in the book, you can put it through a program where you can calculate how many rectangles you want. And look, in the very beginning, you can kind of see the same kind of idea where the left sum and the right sum have pretty relatively different, drastically different values. And then the middle estimation is always usually in the middle. But what I want you to really take a look at is what happens as I subdivide the interval that I want to calculate the area under into 10 rectangles. The numbers kind of get closer, and then if I calculate up to 25 rectangles, imagine all the work. And here, remember, in ours, we did what? In this one, we did 3 rectangles, and we did this one took 5 rectangles, and see how much more work this came out to be because due to the fact that the heights were determined by a much more complex function. Okay. if you can only imagine, this is not a easy parabola. This is, in fact, x squared sine x. That's a lot more complicated to plug in at many different intervals, right? But this program made it a little bit easier by putting in way more rectangles than I think humanly possible to calculate by hand. Look at by the time it gets to 1,000 rectangles, and look how much closer the values are. So as you can see, if you make a lot of rectangles, more of those rectangles are going to actually fit under the curve, as opposed to having wildly generic rectangles that overcompensate or underestimate. Overestimate or underestimate the values that are under the curve, right? But as you can fit more and more rectangles in there, you're going to get a much more accurate representation with either the middle sum, left sum, or right sum. Okay, it's usually a safe bet to go the middle road, the middle sum. But as you can see, at some point when you have many rectangles, it really almost doesn't matter. It's negligible, the differences. Okay, so that's one huge concept I wanted to kind of go over with you guys. Let's see, anything else in here? All right, I think that's about everything so far. Trying to go over anything else that maybe we should go over. Okay, I think that's actually all I wanted to discuss with you guys. But if you guys need help with any of these problems, oh, and I think I can remember now. If there is any problems that involve using a calculator, I think I took them off this year's cover sheet, but in case I still do, they involve you programming in the program for the, like, I have you programming in a program and putting in how many rectangles. Disregard that. You're not going to need that. In fact, in the next week of content, when we're learning about integrals and antiderivatives, this method is going to seem very archaic, and you're not going to be using this anymore. However, it really helps to know and understand the concept of where integration comes from. And if you really are going sequentially in terms of these videos right now, meaning you're going from one lesson to the other, and the next lesson builds upon the previous lessons, then you're not going to know what integration even is at this point. But if you do, then maybe you kind of have an idea of what I'm talking about. But if you don't, just keep in mind that integration is really going to make this method a lot more inefficient, but you do need to understand where integration will come from. Remember, I boiled down the first year of high school calculus AB, essentially the first semester of calculus that's usually taught in universities. The way they organized and structured is usually just learning what the idea of a derivative is, which is a slope at one point, and integration, which is area under the curve. It's calculus in the first year semester basically boils down to just that, derivatives and integrals. So right now we are building our case. We've been dealing with derivatives. We're slowly going towards understanding how to estimate the areas under the curve in a much more efficient manner. Okay, so be prepared for that on the horizon. And as well as that, if there's any problems in here that ask you to use some kind of weird calculator program to do this, please disregard that if it's still in the cover sheet. Okay, but I think I took them out. And then if you're having any difficulties with rotating these, I think I took most of those out as well. But if there's still any problems with rotations of Riemann sums, or like rotating over the x-axis, okay, if you can imagine how crazy that's going to look, please come to tutoring for that. But I think I already eliminated those as well. I think that's a little bit ahead of where we should be right now in the school year. Okay, guys, thank you guys for tuning in. You guys have a great day. Bye.